Yeah, good morning, participants and respected the coordinator, Professor Gayadhar Panda, so who has been with me for past 5 years as one of the good collaborator and my mentor as well. And so thank you, Professor, for inviting me to deliver a talk for this ATAL FDP, relevant to the renewable energy integrations. So yeah, my slides are completely visible, right? It's a full screen mode. Yes, participant, anyone
Yes,
can just,
sir.
yeah,
Yes, sir.
yeah. Actually, I kept it in the full screen mode, so I may not, able to find your, the information on the chat box. So if someone is, if the slide is not visible or if I'm not audible, please can, unmute and you can respond so that I can understand accordingly. Okay, yeah.
Yes, sir.
Okay, very good morning. Participants, and thank you, Professor Gayadhar Panta, who has invited me for delivering a talk for this proposed ATAL FTP. And thank you, Professor. And it is my pleasure to contribute as the session speaker for this proposed FDP. So my area of research is advanced control strategies for grid-tied solar PV system. As I'm an assistant professor at Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram, Chennai. As I had been with this institute as an assistant professor since June 2018. So prior to that, I was with the University of Nottingham, UK. Malaysia campus as an assistant professor in the Faculty of Engineering. And so my career started at 2007 while I joined as an assistant professor at National Institute of Technology, Rourkela. As I served as an assistant professor, from 2007 to 2013. Then I left NIT Rourkela. I have gone for a postdoc in the Europe. I did concurrent two postdoc in the Europe. Then after I joined at Nottingham. So for the finally, I come back to my destiny, what is called the IIITD&M Kancheepuram. So as I'm associated with the EC department, and however, I have developed the photovoltaic research laboratory here with the help of funding from DST SERB. So I have developed a 1 kilowatts grid connected solar PV system, and I have established the laboratory as well as I could make an excellent collaborations with the MNIT Jaipur as well as SVNIT Surat and the NIT Meghalaya as well with the Professor Gayatha Panda. So we could make a variety of control techniques for grid-tied solar PV system, and we could publish in the top tier journals like IEEE as well as IIT in the past couple of years. That so I wanted to disseminate the knowledge in the area of control strategies for grid-tied solar PV system. And the outline of my presentation include what the renewable energy contributes in the Indian growth in the energy sector, and what would be the fundamental concept of solar PV system, and the objectives of my presentation, and including the schematic of grid integrative solar PV system, and what would be the subsystem for overall schematic of grid interactive solar PV system that include the control circuitry as well as the power circuitry. So how each subsystem has been, designed and that has been fabricated in the laboratory prototype, and further, so how we have, investigated the advanced control for integrating a solar PV system with the utility grid, and so how that has been experimentally validated in the laboratory prototype with the help of DSpace W104 digital signal processor, and it has come up with certain hardware results as well as the simulation the results that has been validated, so that we could find that there is an excellent convergence between the experimental result and the simulation as well. And so finally I could make the summary of the results what we could able to make or validate in the experiments as well as in the simulation platform, followed by certain the recent references that we able to come across to find the the problem identification in the area of grid interactive solar PV system. Yes, I think let us come to a point of the renewable energy in India. I couldn't be able to attend the inauguration. Maybe one of the eminent Professor Sumar Misra might have been inaugurated the ATAL FDP, the inaugural session. That still he was one of the key motivator for the young researchers like me and all. So let me give an initiative of renewable energy in India. So India is one of the the countries with a large production of energy from the renewable energy sources. Basically, we are the third largest country in terms of electrical power, consumer as well as the power production across the country. That as of 30th September 2020. So the total installed capacity of renewable energy in India is about 36.17 percentage. So that is solely by renewable power generation unit. I mean, 50 percentage was contributed by both wind power generation and solar photovoltaic power generation unit. I mean, around 135 gigawatts of power out of 373 gigawatts by renewable energy sources, excluding large hydro. Right? So, I mean, the target would be around 57 percentage of the total installed capacity from the renewable energy sources by 2020. I mean, according to Central Electricity Authority, Government of India. So, as the Indian renewable energy sector is the fourth most attractive renewable energy market in the world, as I could tell that the India is ranked, I mean, the fourth in the wind power and the third in the photovoltaic power, I mean, as of September 2020. So this was the data during 2018. So 2018, so India was holding top fifth rank in the solar power installed capacity across the globe, and now it has been lifted to third position as of September 2020. So with that, I think you could get the motivation that, so why we promote the photovoltaic power generation in India. So basically, India is located in the subtropical weather, and the throughout the, I mean, here we have, I mean, that excellent, I mean, solar irradiation across the country. That so we are well, I mean, connected with the, I mean, the solar energy, right? Even in the remote area you can find the sun across the year, so that we are able to have an abundance of solar energy. So by installing a solar PV panel, so we are able to convert directly the solar energy into electrical energy, so that can be utilized for the isolated communities in terms of the standalone system, or maybe we can generate the bulk amount of electrical power and to feed power to the utility grid, right? So the key technology, and the professor, I mean, the BK Bose, one of the eminent professor in, I mean, University of Tennessee, so he has pointed out that there are two key technologies playing a very major role for the community in the 21st century. And the technology one is the information and communication technology. And as you might be knowing that how this ICT is playing a very major role in, I mean, in the communities, as you might be knowing that how, I mean, that the mobile phone has created an impact among the community as well as the internet, right? So that the technology is going towards that e-commerce as well. In addition to that, the technology called renewable energy sources and material science is also playing a major role. That is called the second, I mean, the technology is playing a major role in the 21st century, right? So thanks to, I mean, renewable energy, I mean, sources, as you might be knowing that with the very global, I mean, pandemic situation that we are in the isolated, I mean, the remote areas, that we could be able to, I mean, make the session very virtual or maybe in the form of online. So the impact, the natural disaster or maybe a global warming or the climate change. So it, I mean, it creates a certain impact among the, I mean, the community as well as the social need. So how this renewable energy is trying to, I mean, mitigate such global warming as well as the greenhouse effect. As you might be knowing that 60% of the total installed capacity was solely met by a coal-fired generating station like a thermal, right? So that was the scenario during 1980s. So actually during 1980s, what happened? There was a oil price shock across the globe. So they were thinking of an alternate, I mean, to promote the renewable power generation. I mean, still you might be knowing today, I mean, you can see the petrol price that about 85, 86 rupees as of today, that there is a great impact on the, and the fuels, and especially that is very expensive due to transportation. The countries like India, still we import the fuels for the, I mean, the vehicle, I mean, automobile. So that is the thing. So that the expensive, the prices are, I mean, increasing very exponentially. And moreover, the global economy is also depleting due to this global pandemic. So with that, the renewable energy is trying to, I mean, the across the globe, so we promote the renewable power generation to meet the future energy demand as well as the mitigation of global warming, including climate change. So with that, thanks to the technology like renewable energy sources. Among two renewable energy sources, as you can see that the solar power and the wind power. So basically, they are the large scale power generation unit. So they exclusively used for the, I mean, the multi-megawatts power generation system. As of September 2020, so the total installed capacity of wind power across India is about 38,124 megawatts of power, and the solar power would be around 36,050, I mean, megawatts of power. So ultimately, it is both contributes about 60% as well the total installed capacity in the renewable energy, excluding the large hydro. So the total installed capacity was about 89,229 megawatts as of September 2020. So the target would be after a couple of years. So the total installed capacity would be around 175,000 megawatts of power. I mean 175 gigawatts. So with that, the key technology is, I mean, the renewable energy is basically a wind power generation and the solar power. And slowly the solar power generation is coming up. If you could see the renewable energy development in India, so India was holding top rank in the wind power generation during 2000, 2010. With the large, I mean, decade, since 2010, there was a huge development as well as the investment in the solar power generation and the solar power installation across India. I mean, with the initiative of Ministry of New and Renewable Energy. So now, I mean, the solar power is totally dominating in the energy sector, even not only in India, across the globe. So it is going to take over and dominate the wind power generation in another couple of decades, right? So the solar power in India, as I told you, is a fast developing industry. The country's solar installed capacity was around 36,050 megawatts as of September 2020. So it's totally going to dominate the renewable energy sector in another couple of decades. Even not only, I mean, the solar, I mean, the power is dominating in Indian energy sector and across the globe, everywhere. I mean, even the countries, especially in the Western countries like Denmark and Norway and Netherlands, even in Canada and Australia and I mean US. So this solar power generation is it created the I mean the large impact for the I mean the electricity generation. Even there is a country like the Denmark, even still they promote the renewable power generation based on wind energy system. So as by their target would be around by 2050, they would be, I mean, fossil fuel independent. So the total installed capacity will be solely made by wind power generation. That is what the resolution by the government of Denmark as well. So that you can understand that how the, I mean, and the impact has created among the communities in terms of renewable power generation system. So as we promote the solar power generation system in the 21st century, as it totally dominates in the energy sector. So as you might be knowing, the very major advantage of the solar photovoltaic power, basically, it is the installation as well as the commercialization as well as the design of the solar PV cell is very simple. And I mean, moreover, the investment time would be very shorter as compared to the the wind turbine installation and commercialization. First of all, and you might be knowing that so the photovoltaic power generation simply involves the use of the simple PN junction solar semiconductor diodes. So that it basically converts the light energy into electrical energy directly without any energy conversion or without any intermittent energy conversion. So that is able to generate the light energy into electrical energy very directly, right? So that is what this is a simple static device that is able to generate electricity by the principle of photovoltaic effect, right? So it's a very simple form of energy conversion. And the solar PV model is a highly modular, and hence the plant economy is not a strong function of the size. So that can be easily installed in the site wherever you could find the solar, energy potential is abundant. There you can install the solar PV, so that do not take much time. And moreover, the environmental impact, as it is static power generation, so it doesn't cause any, the noise, or it is not harmful to the environment as well. And moreover, the power output matches very well with the peak load demand. This is one of the, the beauty of solar power generation unit. That is why during 2012, and there is a proposal invited by Ministry of New and Renewable Energy. So in terms of hybrid energy system, especially solar and wind power generation system. And if you could see the characteristics of both wind power and the solar power, and the wind power basically, it is suitable for the base load throughout the year. And as the output power generation is having cubic relationship with wind velocity, and whereas in the PV power generation, it is suited for the peak load demand during hot summer. So that is what throughout the year, combination of solar and wind can have an excellent choice for the power production in terms of bulk power. So that is what they have floated the the funding, from Ministry of New and Renewable Energy. So the power output characteristics well matches with the peak load demand, as the response is basically like a bell shape. And moreover, as it doesn't have any, the movable part. It is basically a simple static structure, as it has a simple, P-type semiconductor and N-type semiconductor with a large, heavily doped depletion region. So that PN junction solar cell is exposed to the sun or the solar energy, so that directly convert the photons into electrons, right? So the principle is very simple, and moreover conversion is very straightforward. So it do not have any moving parts, and hence no noise, and high power capability per unit, per unit of light. So that is what, thanks to the material science. So now, due to development into material science, even there is a multi-junction solar cell or the heterojunction solar cell, it has come into picture. So we are able to convert light energy into electrical energy at a high efficiency, even at 30% or more, 40% as well. So there is a, the compound semiconductors. So that has been in the practice for past couple of years. That so maybe in after a couple of years, you can find the the PV cell industry with multi junction solar cell or the compound semiconductor solar cell that has been practiced maybe in after a couple of years. So the longer life with a little maintenance, of course, it doesn't have any movable parts, so the maintenance quite free, but still there is a problem associated with the solar degradation, as that is a problem that still they're investigating to improve the solar cell performance. If the to enhance the lifetime of the solar cells, and highly portable because of lightweight. So these are the major advantage of photovoltaic power generation. So the trend is towards the solar PV, right? If you could see the value chain for the photovoltaic energy, as I told you, the PV cell is a simple, the polysilicon material that it is originated from the silicon, as it is, abundant in nature. So we are able to, manufacture the PV cells with the help of the silicon melting and the ingot glowing. So we are able to make the solar, the vapor, right? So then with the help of this silicon melting and the ingot glowing, and we are growing, we are able to manufacture the PV cell, the photovoltaic cell, and so that can have a P-type and N-type semiconductor that has been fabricated in the single silicon growth, and it has a heavily doped depletion region between N-type as well as the P-type. So whenever the sun is whenever the PV cell is exposed to the sun, and ultimately there is an electron hole pair recombination, and hence it constitutes an electron and flows from N type to P type, and hence there is an electron current. So whenever you connect an external load across the PV cell, then the current flowing towards the load, so that we are able to convert light energy into electrical energy directly. And basically, it converts light energy into DC electrical energy, as it is basically converting a DC power, right? And combining a PV cell in the form of series and parallel combination to have a required amount of power, then the PV model is fabricated, right? So then the PV model can be installed in the site, having the series parallel combination to have a required amount of power rating, and we form a PV array, right? So that can be installed in the rooftop, so that yes, there is a noise. Dear participant, please mute your mic. Yeah, and the PV model can be installed in the series parallel combination in the rooftop, so that we are able to have a building integrated PV model, so that we can forward all electrical appliances that has been used in the home. So that is what this may be an grid connected or maybe a standalone system. That the PV solar PV system, the building integrated PV can have a combination of the PV array and the PV inverter, battery, support monitoring system, including the installation. Right, you can see the concept of PV cell, as you might be come across during your undergraduate or maybe during masters, that it has the N-type semiconductor and P-type semiconductor, and it has been separated by a heavily doped depletion region, right? So when the N-type semiconductor is exposed to the sun, then ultimately there is a liberation of electrons from N-type to P-type and P-type to N-type. So it will try to try to produce an electron hole pair recombination. There is a current flowing, or flowing from the N-type to P-type, what is called the dark current or maybe a photo current, right? So whenever you connect an electrical load across the N-type and P-type semiconductor, then ultimately the current flowing towards the external load. That is the way the light energy will be converted into electrical energy with the help of photovoltaic effect, right? So you can see that as this is a simple schematic of the photovoltaic effect in the solar cell. That is the way we are able to extract the electrical energy from the solar cell, right? And you can see that because the understanding of fundamental is very important in research and development of solar power generation unit, right? So compromising fundamental or the basic concept, applying an advanced control strategy and the inverter, especially you do not understand, and what would be the, what would be the basics about the solar PV system and why you need control algorithm to integrate solar PV with the utility grids. Of course, you will have confusion in that. So that is what I starts with the fundamental. As you might be knowing that as the simple, solar cell is basically a constant current source as it constitutes an electrical current that can be flowing towards the external load. During short circuit condition, it can have a maximum current, what is called the photo current. That would be a short circuit current. During such situation, there is no voltage across the PN junction. Obviously, the voltage is zero. And when the device is left open circuited, then the short circuit current would be zero. The voltage is at maximum, right? So that would be the voltage that can be generated with the help of photovoltaic effect in the simple PN junction solar cell, right? So the voltage at the normal operating point would be around 0.5 volt in case of silicon photovoltaic or the PV cell. And again, moreover, the current, so that has been generated by the electron hole pair recombination, what is called the dark current or maybe a photocurrent. So that photocurrent, it depends on intensity of the irradiation or the insolation. You're right. As you are converting the photons into electrons, of course. So the state of art in the solar energy, basically, it is, in the state of two parameters called the temperature and irradiation, right? So you are converting such irradiance into electrical energy in the form of electrical current. So that the short circuit current or the maximum short circuit current is directly proportional to the intensity of the insolation falling on the PV panel, and also depends on the size of the cell, right? And moreover, the open circuit voltage as the voltage across the PN junction when the device left open circuited, right? So that depends on the temperature. And always, the solar cell that performs well, that can generate maximum possible power at high irradiance at low temperature. That is what the thing. So you can see that as the insolation or the irradiation decreases, then obviously the short circuit current generated by the solar cell is very low, and hence the power production is basically the multiplication of current and voltage. It would be very minimum. That is what solar cell, it generates a maximum possible power at high irradiance and low temperature, because at low temperature the voltage across the device is maximum. So the multiplication of voltage and the maximum open circuit voltage and the maximum short circuit current, it gives the the practical maximum power by the solar cell. And if it see ideally the maximum power, it would be the multiplication of VAC and IAC. That is what you can find the area under the curve, right? So that area under the curve, that decides the performance of the solar cell. I told you that the solar cell, the light generated current, that depends on the solar irradiance as well as depends on the cell size. So that may have a current rating would be around 4.95 ampere or 5.55 ampere. That depends on the irradiation. As we could take for the theoretical study, even in the simulation, we could take the standard test condition, includes the irradiation of 1000 watts per meter square with the temperature of 25 degrees C, right? So as the irradiance increases, then the the photo current or the short circuit current increases linearly. And moreover, that depends on the cell, material, then the open circuit voltage that produced by the solar cell, it would be around 0.5 volt for the silicon semiconductor PV cell, all right? And this is the simple characteristics that you can see the theoretical maximum power would be the multiplication of 0.62 and 5.5 ampere. But practically, any solar cell that has been installed at the site, that can give the maximum power of multiplication of 4.95 ampere with respect to 0.49 volt. So that is the practical maximum power. So the ratio between the theoretical maximum power divided by the practical maximum power, multiplication of IAC maximum and V, I maximum and V maximum, that gives the factor what is called the fill factor. So the fill factor is the measure of the squareness of the curve. Okay. So if the curve is converging with the point to 5.5 ampere and 0.62 volt, then the area under the curve is going to be large, and hence the fill factor would be approaching unity. So always even in the theoretical maximum limit, according to second law of thermodynamics, the fill factor never be equal to 1, as it is a measure of the quality of the solar cell. So as it gives the squareness of the IV curve, so that someone should have an idea. And as I told you that as the area under the curve, I mean VP max and the IP max, that has to be converged with the point, I mean the open short circuit current and the open circuit voltage. That never happened even in practical condition, right? So basically the solar cell converts light energy into electrical energy. Of course, the conversion efficiency is very low. So it doesn't mean when the solar cell is exposed to the sun, there is a strong, I mean, recombination of the electron hole pair recombination, so that it can constitute high amount of current. Absolutely no. Ultimately, there is a huge loss due to electron hole pair recombination. So then the conversion efficiency not even 15% for the, I mean, the commercial PV area that has been installed in the practice, right? So ultimately, we should have a power conditioner device. So as it converts photons into electrons, so that we wanted to extract maximum possible power. So we have to have a, I mean, the power conditioner between the electrical load and the solar cell, right? And you can see that. So the practical IV curve. So the practical IP max multiplied with the VP max, that has to be, I mean, in line with the point what is called the P max. That is what is called the power at a maximum power point. So that has to be, I mean, extracted, that has to be defined in the equilibrium position whenever there is a changes in irradiation and temperature, right? So we should have a, there is a power conditioner or interfacing device, so that we are able to match the resistance of both load as well as the device. So that is what it has to be done with the help of power conditioner device. So that will adjust to be the most suitable voltage and the current automatically, that we are able to extract maximum possible power. I mean, so the power conditioner is basically a simple power electronics converter, say DC to DC converter. So that has to act as the, I mean, the impedance matching device or the resistance matching device, so that it is automatically adjusting the resistance of the, I mean, the load as well as the device, so that it can satisfy maximum power transfer theorem, so that we are able to extract maximum possible power. So this is one of the important, important device that has to be interfaced between the solar PV cell and an electrical load. So you please keep in mind that. Moreover, the solar cell output parameters, I mean the solar voltage and the solar current, it largely depends on the input parameter, what is called irradiation and the temperature, right? So the as it has a nonlinear characteristics between the solar, I mean the current and the solar voltage, so that this cannot be directly connected with any electrical load, or this cannot be directly connected with any electrical grid as well. Ultimately, the power protection is unregulated, or power protection by the solar PV cell is uncontrollable, so that it can't be directly connected with any electrical load. As the electrical load, it needs the constant voltage across the load, I mean throughout the range, right? So you can see that it has to match the characteristic resistance, what is called the, I mean, voltage divided by the particular, I mean the current, so that we are able to define the, I mean the resistance, what is called the characteristic resistance. So if the load has a 0.05 ohm, I mean resistance, then we can extract the maximum possible power with the 10, I mean multiplied by 0.5, so that would be around 5 watts. So that is the way you can design the power conditioner system, so that you are able to extract maximum possible power, right? And not only that, as you are installing the solar cell, as you might be knowing that the PV model or the PV panel is basically the series parallel combination of the single silicon PV cells. So by connecting in parallel, we can enhance the current rating. By connecting in series, we can enhance the voltage rating, so that you can design a PV model or the PV array for the required power rating. So that can be installed in any field for, I mean, bulk power protection, right? So as I told you, the current produced by the solar cell, basically called the photo current, and it directly proportional to the irradiation. And if sudden increase in irradiation, ultimately there is a non-uniform current produced by the solar cell. And moreover, as it has a series parallel combination of the solar cell, if the installed PV panel is hidden by the kind of a large building, and ultimately there is a mismatch in the irradiation falling across the PV cell, so that it can cause the circulating current or mismatch the current flows between the two, I mean PV cell, it would be a mismatched. So due to the mismatch, and there is a, I mean, potential gradient, and it constitutes a local circulating current, so that may damage the diode, right? So in order to provide an alternate, I mean, path for that, the circulating current, we use the practical PV, I mean the solar panel uses a bypass diode. So that is also very important in the practical, practical installation of the solar PV panel. So that has to be taken care of. And moreover, it doesn't mean the irradiation falling on the PV cell, it would be uniform, because that depends on the climate change. As you might be knowing, maybe during morning, you can have a uniform irradiation at temperature of around 25 degrees C. And during afternoon, maybe the irradiation will be very high, and moreover, temperature would be very high. That is what the characteristics of the solar cell is basically intermittent. So as the characteristics, it largely depends on the input parameter of the solar energy is an irradiation and temperature. So that varies throughout the day. So the power production is not uniform, and the power production is basically varying. That is a rapidly varying power source. So that is what it cannot be directly connected with any utility grid, or it can be, connected with any local load as well. And you can see the parameters which affect the performance of the solar cell is basically a temperature. As you might be knowing, all semiconductor devices, the performance degrades if the device is working at a very high temperature, as you might be knowing, right? So we can have a different type of solar cell, basically a crystalline solar cell. It may be a monocrystalline, or maybe a polycrystalline, or it may be a amorphous silicon cell, or maybe a, thin film. So you can see that as the temperature increases, then efficiency of the solar cell decreases. And you can see that at the 100 degrees C, obviously the efficiency, it would be around 8%. It implies that huge amount of power loss when the solar cell is exposed to the sun at a very high temperature. That is what, even if someone feels that if the temperature is very high and we are able to generate more power, absolutely that is a wrong concept. So solar cell can have an excellent performance for power production at low temperature and high irradiance. So that is why this has become very popular renewable power. So power generation even in the Western countries. And if you could see, there is a country called Norway. In Norway, throughout the year, even hardly 10 or 20 days only they find the sun, right? So throughout the year, they do not find the sun, but still they install the number of, the PV panel in the rooftop, as well as they installed for, the power generation. Still they work fine, because the solar cell performance, it largely depends on the irradiation falling on the solar panel, right? So the solar current is directly proportional to the solar irradiance. So so that ultimately, when the model temperature rise up, the efficiency decreases. Ultimately, we go to have a cooling, by the natural ventilation, so that we are able to maintain the power, produced by the solar PV cell. So that has to be taken care of. That is what one of the factor. So it degrades the performance of the solar cell. Okay. Another important point I wanted to, bring here, that even solar cell, and now it has been, it has been, model, and it is under practice with the bifacial solar cell. The beauty of bifacial solar cell is that, if you see the commercial PV cells or the PV panel that has been, installed at the any site, it has only the PV panel on the top of the plate, right? So when the PV panel is exposed to the sun, and ultimately you are converting that light energy into electrical energy, right? But now there is a solar panel is going to be commercialized. It is under development, called the bifacial solar cell. So what the bifacial solar cell, that in the PV panel, so then the PV, the cell is, fabricated on, top as well as bottom of the plate. Now what will happen? So if the top of the, plate is exposed to the sun, so it is able to, convert light energy into electrical energy, and still the bottom of the plate is also having the PV cell. Then what happens? If such a solar cell is installed in the Western countries where the snowfall is very heavy, now what happens? The surface basically having the snowfall, that surface is an excellent candidate for reflecting the irradiation. So now what happens? So you can install such a bifacial solar cell in the Canada or in the Western countries like Norway or Denmark. Now what happens? When the irradiation is falling on the snowfall and in the floor, ultimately that irradiation will be reflected by the snowfall. Then that will be, exposed to the bottom of the plate, so that you are able to, generate electricity by bottom of the plate as well as top of the plate, so that overall efficiency will be doubled. That is what the concept has come into picture, what is called a bifacial solar cell. So this is under development. So what I mean is, solar cell able to generate electricity at high irradiation and low temperature. And please keep in mind that is what. So the solar degradation can happen, and whenever the device is exposed to the high temperature. Okay, thank you very much, dear participants. And if you have any doubt, or if you are unable to hear my voice, you please interrupt with me so that you can unmute and give your concern, and accordingly I can try to rectify the problem. Because I assume that you are an active listener, and moreover you could be able to, I mean, follow me. That is very important thing, because this I mean, online session or online presentation, obviously it is not a two-way communication. So obviously it is like a one-way communication. But still, I believe that the content and what I could deliver, that gives I mean, certain insight. I mean, on the grid interactive solar PV system. So please, try to, listen to my lectures, and if you're unable to follow me, and please let me know that, and accordingly I shall try to, rectify the problem. But I assume that you are listening, because I could see, I could make the full slides view, so I do not find, your comment on the chat box, as well as I do not, find anything if you do not respond. Okay.
Sir,
Yes.
we have
So
requested all the participants to post the question in the chat box. So we'll take all the
okay.
question at the end, sir.
Yeah, that would be more good. That would be more good,
Yes,
because
yes,
I do
yes,
not
sir.
see any, the question right now, as I kept it in
I
the
will read
preview
for you
mode.
all the question at the end, sir. No problem.
Yeah. Thank you very much. And so we shall have, another, 1 or 1.5 hours about this great
Sure,
interactive
sure,
solar
sure.
PV system. Okay. Yeah, thank you
Sure.
very much. So I have highlighted the certain important point of the solar PV cells, understanding the fundamental. I mean, the physics of solar cell, that the solar cell is basically a simple PN junction, the semiconductor diode having the large depletion region. So it is able to convert light energy into electrical energy very directly. It has many features, that it is one of the emerging and green energy source for large scale power generation system. And moreover, I mean, it also mitigates the global warming, as well as the greenhouse effect. And moreover, we discussed about the fundamental. I told you it is converting light energy into electrical energy, and it has certain non-linear characteristics between the output as well as the input. As you might be knowing, any electrical system output, it largely depends on the input, and the output is basically a time dependent on the input parameter. So as the input parameters are basically a temperature and irradiation, so that output parameter of the solar PV cell is basically a open circuit voltage and short circuit current. So it largely depends on the input parameter. So as the input parameter is an unregulated one and uncontrollable, and obviously the output varies. So basically the characteristics of the solar PV cell as system is basically a stochastic in nature. Obviously there is an uncertainty at always. So I mean, extracting the power from the solar PV cell is still, it is straightforward, but I mean, it is not efficient. That is what I mean, as an electrical engineer, we need to use the power conditioner to extract the maximum possible power by satisfying maximum power transfer theorem. So that is what we use, as it is converting a DC, I mean, light energy into DC electrical energy. Obviously, we use a DC to DC, converter for conditioning and electrical power, that must be regulated, right? So let us talk about the PV cell technology. And the solar cell, it can have, either single silicon semiconductor, or maybe a compound semiconductor, or maybe an organic semiconductor. I mean, as far as single silicon semiconductor is concerned, and it is basically classified into crystalline as well as a non-crystalline. So non-crystalline solar cell, basically an amorphous, the silicon cell having the conversion efficiency about to 10%. And the crystalline solar cells are very popular. So for fabricating large scale power generation PV panel, and having the conversion efficiency of single crystal about 17%, and polycrystalline would be around 13%. And basically it is a, it is a conversion efficiency. It's a theoretical. Still, the commercial PV model having the different efficiency. Obviously, you might be knowing there is always a difference in efficiency of commercial PV model as well as the laboratory prototype, right? And the compound semiconductor is basically with, gallium arsenide as indium phosphide, having the conversion efficiency up to 30%. Still, it is under development. Especially, there is a problem encountered in the fabrication. And moreover, organic semiconductor like a dye sensitized type or organic thin film layer type, still the conversion efficiency is very low. So very popular solar cell, basically the technology we use is either monocrystalline or the polycrystalline. Even I could point out another important, the latest development in the silicon cell, solar cell, as we use a bifacial solar cell, as it can have a conversion efficiency of 2 times as compared to the conventional, say, mono, silicon cell. So as we use the bifacial, so there is a power, extraction on the top as well as bottom of the plate, and that is one of the best choice or the best candidate for extracting power in
Excuse me,
the.
sir.
Yes, please.
Sir, just participants are requesting just to hide that pop-up button, sir.
I see. Okay. Is it okay now?
Oh, yeah. Thank you, sir.
Okay, thank you. So the conversion efficiency is basically electrical energy output by energy of the insolation on the solar cell. As the for bifacial solar cell, still the conversion efficiency is double as compared to the a single facial solar cell. And also, if you talk about the research and development in the solar cell, still the modeling of solar cell itself, it is a great task because, and whatever we could see the IV characteristics, basically it is a highly non-linear. As you know that at a volt, the current is maximum. At a zero current and the voltage is maximum, it always having intermittent and non-linear characteristics. So that it depends on the input parameters called the temperature and irradiation. So mathematically modeling the PV panel and the characteristics at par with the data sheet, that is very difficult. That is what the many iterative method has to be used so that we are able to able to find the unknown parameters and the what the parameters are not available in the data sheet, so that you are able to solve that nonlinear equation of the the PV cell current. Accordingly, you can mathematically model the device. That also another area of research and still further discuss at the end of the session. This is the hierarchy of the PV system, that single silicon solar cell having the power extraction of 2 to 3 watts, then that can be combined in series parallel formation, so that we are able to design the PV model or the panel with the 200 watts with 9 and 6 series parallel combination of the single solar cell, and further that can be connected in the series parallel formation. You can have a PV array that can be installed in the site to extract the power of up to 50 kilowatts. This is what, and you can see the how many number of modules are connected in series parallel. This is the hierarchy of the PV system. But a single silicon cell can have a maximum voltage generation of DC voltage of 0.5 volt with 25 milliampere. Please keep in mind that. So we are able to design a solar PV system with the required amount of power by connecting series parallel combination of the model as well as the panel, right? So let us talk about the composition of the photovoltaic system. As the PV array is basically a nonlinear element, that it can have a the intermittent characteristics, as it depends on the input parameters called temperature and irradiation. Ultimately, we should have a power conditioning device as it condition an electrical power that is being extracted from the PV array, right? So the PV array output power is basically a DC power that has to be conditioned to convert such unregulated DC power into regulated AC power that can be fed into the utility grid. Obviously, it is acting like an inverter, or still that can be converting uncontrollable DC into controllable DC that can be fed into the local load. That may be a standalone system for the lighting purpose, or maybe any industrial or any standalone house as well. So as it needs, either it can act as a DC to DC converter or DC to AC converter, as it has a different topology, and moreover it should have a monitoring system for transmission as well, so that monitoring as well as protection can be enabled in that solar photovoltaic system. And that, as you can see, it composed of inverter as well as the series parallel combination of the model, and it has a peripheral component, basically the balance of the system, that support for model installation as well as the battery. So battery is invariably used in the standalone system, so that can support for the voltage as well as the frequency. So when the system is under isolated condition or when the system is under off-grid condition. And moreover, the power conversion device, as we use the power conditioning device, depends on the topology and the components, so that can have a different configuration, so that you are able to integrate such a PV array with the utility grid. And the key motivation about this, the grid integrative solar PV system, as I told you, the PV power generation is highly intermittent and is basically a disposed power generation. So the output characteristics are, it varies with respect to the input parameters like a temperature and irradiation, so that it can't be directly connected with the utility grid. As thanks to power electronics, so power electronic converters are invariably used in the renewable power generation for integration, because so the integration is very essential, to meet the grid code requirements, because as you might be knowing, as we use the power converters between the solar PV system and the utility grid, and that has to satisfy the grid connection requirements. That is what. So every country has started to have their own grid code compliances that has been imposed by power system operator or the transmission line operator. So while integrating solar PV system with the utility grid, almost all the countries like Canada or US or France or Ireland or Denmark or Norway, or even China, they have their own grid code compliances. And already in India, we started to investigate on the grid connection requirement to integrate and solar PV system with the utility grid, right? So that integration is possible by interfacing a power electronics converter between solar PV system and the utility grid. So power electronics converter is a candidate who provide an asynchronous interface between solar PV system and the utility grid. So the key consideration of integrating solar PV system is basically to design and operation of the power converter to achieve high efficiency for different power configuration. So the requirements for power, the power converter connection, it include maximum power extraction and high efficiency, controllable active as well as reactive power injected into the utility grid, and it should have a total, lower total harmonic distortion of the grid current, and it should have an excellent transient response during grid abnormalities, and it also include the grid synchronization. I mean, the inverter output frequency must be well synchronized with the grid frequency so that we are able to integrate, a solar PV system with the utility grid through power converter. So consequently, the integration of solar PV system with the utility grid, that it largely depends on the performance of the converter, which is being used to interface solar PV system with the utility grid. So that is why the converter is what is called the grid interactive power converter. So he is a candidate to provide an asynchronous interface, right? So the performance of such converter connected to the grid, it largely depends on the control strategy being applied, because you are trying to inject and controllable active as well as the reactive power into the utility grid. So how the control requirements are going to be met, that purely depends on the control technique which is being employed on the grid interactive power converter, right? So how the control strategy, it satisfies the above set requirement. That is a very important motivation. So you can see that even in the strong research team from even NIT Meghalaya, including our Narendra Babu and two or more, the scholars at NIT Meghalaya, they're actively working on the research theme. So the integrating photovoltaic power system with the utility grid is a very great task. It should be further investigated. And the considerable feature of the power converter, the change of environmental condition, that the temperature and irradiation changes very rapidly, and even still the PV array is, it is largely affected by the partial shading as well. So extracting the maximum possible power from the PV array during such situation is very difficult, and it should be further, investigated. And moreover, the response of environmental change. So tracking maximum power point during such situation is very difficult, and ultimately that has to be done with the help of a power converter. And the synchronized operation with the grid is a very important concern while integrating solar PV system with the utility grid. And the protective function, inverter protection from the grid fault condition and grid protection from the fault condition of the solar energy system is of a great interest. It should be further investigated. So nothing is straightforward. You see, simply using the converter, it doesn't mean you are integrating solar PV system with the utility grid. It has the different challenges. So that challenges has to be encountered, that has to be defended with the help of the power converter control, right? So the objectives of the research and what our team has done, and we have implemented a different advanced control strategy for grid-tied solar PV system. So the detailed description of the design, development, and implementation of grid interactive solar PV system is presented here. So for that, elaborate prototype of three-phase four-legged inverter is designed and is used for the PV system. And the proposed three-phase four-legged inverter that can act as a multifunctional inverter, so that it is able to independently control an active as well as the reactive power for voltage, frequency as well as voltage control. And also it serves as an active power filter for mitigating lower order harmonic, which is being injected into the utility grid. So not only controls an active as well as reactive power, it also acts as a shunt active, active power filter, so that overall system performance is enhanced. So in addition to that, as we proposed an adaptive phase locked loop for the synchronization with synchronization of the inverter with the utility grid, so that it is able to provide an controllable active as well as a reactive power by generating precise reference current. The reference current generation in a precise way is very important to implement your control algorithm in an accurate manner. That is what. So any control algorithm being employed in any power converter, So the very important concept is to implement is to generate the reference current in a precise manner. Moreover, the reference current generation, it should be for fundamental component. That is what is called the active current component. So that is very much essential because we are in a position to control the frequency, right? There are two key parameters that decide overall power system security and power system reliability. So power system reliability, it largely depends on the voltage profile at the point of common coupling, and the power system security, it largely depends on the frequency of the utility grid. So that has to be controlled in an independent way, right? So, and not only that, the proposed control system, it provides the power quality improvement features such as the source current harmonic suppression, load reactive current components, and the zero sequence harmonic current compensation under non-linear as well as unbalanced power electronic based load. And not only that, as we use the solar PV array as a source of power, it also contributes for active power sharing to have an excellent energy management. So these are the important objectives. As you could see that the power electronics converters, so that has been used as an asynchronous interface between the source and the load. Basically, it is a bridge to connect the intermittent energy source with the load, and the load is also, again, it is dynamic in nature, right? So it is enabling technology that provide an asynchronous interface between DC as well as AC electrical system. Basically an example of interconnection of two asynchronous or maybe DC to AC conversion. So that is required to connect a fuel cell or maybe battery to the utility grid. Ultimately, the converter can act as a DC to AC. See the listing of power electronics application. You can find power electronics everywhere thanks to power electronics, such as solid state control, element that provide an efficient energy efficient, the control on, all aspects. If you see that the power electronics, so there is a great era of power electronics during 1980s and 1970s, because the 60% of the total power being consumed by electrical machines in the industry. Now the scenario has been changed. So not only the industrial automation or energy efficient electrical machine we use, even in the even in the smart building as well as in the smart home, we use number of electronic load. Talking about your mobile phone charger up to multi-megawatts wind turbine system, we invariably uses power electronics. So if you can simply say that no power electronics today, ultimately no existence of today's power system. So we invariably uses power electronics. It became a part of power system. That is what. If you wanted to improve the source dynamic, you go to have a power electronics. You talk about the photovoltaic. Ultimately, it uses a DC to DC converter to extract maximum possible power. That is what. If you wanted to improve the load dynamic, say adjustable speed drive, we invariably uses an inverter to control to provide an precise control of the speed as well as torque of an induction motor drive, right? So you use it in the distributed generation, the renewable power generation, fuel cell, or maybe an energy storage, another one important thing. So the energy storage is going to play a very major role in the future energy scenario, as the sources are highly intermittent, providing an excellent energy management to meet the future energy demand or to provide uninterrupted power. Energy storage is invariably used. Even you can say that in the standalone PV system, that can't be, used in practice without any energy storage. So we invariably uses energy storage. So thanks to the battery. So battery is a candidate that is going to play a major role in the future energy system. And most of the loads are power electronics based load. The adjustable speed drive, we invariably uses power electronics, and also used in the power quality problems. To mitigate such power quality problem as a dual feeder or uninterrupted power supply or a dynamic voltage restorer. There is another, the class of devices called the DSTAT can still be used in the, in the supply side to improve the power quality. And moreover, that also can be used in the transmission as well as distribution side. For bulk amount of power over long distances in the form of HVDC transmission. Still, we invariably uses power semiconductor devices. Such as the FACS devices, flexible AC transmission. Devices. For improving the stability as well as to improve the voltage profile in the form of series as well as shunt compensation. These are the different listing of power electronics. And talk about the barriers and challenges in today's power system. The power system is highly complex in nature. So power system is highly complex in nature, electrically, mechanically, and thermally. It has a number of parameters, basically non-linear parameters. There is an uncertainty, and finding the solution for such system is very difficult. That is what. So fully coupled dynamics of generation, transmission, and delivery. And moreover, the today's power system, the system stability is overwhelmed by slow and electromechanical or electrochemical dynamics of the sources. I could read in the recent article that So battery is an excellent choice for improving the transient response. Fuel cells is an excellent choice for improving the steady state response. So if you talk about the fuel cell based power generation, as it do not have an excellent transient response, so for any sudden change in load or when the grid is under fault, it is unable to restore the energy because the dynamic response is very poor, because the fuel cell doesn't have any inertia. But as far as the conventional power generation system is concerned, if you talk about the thermal or hydro, as it can have the turbine, as it basically dynamic in nature, it has the inertia, so it can damp out any oscillation, or whenever there is a disturbance, it is ultimately damp out such disturbances with the help of inherent inertia. Whereas the photovoltaic power generation or fuel cell based power generation, they doesn't have an inertia, so basically their transient response is very sluggish. So that is another the problem what we encountered in today's power system, right? So moreover, we local focus on power electronics. As I told you, during 1980s or 1970s, we solely focus on the load dynamics, as we use invariably adjustable speed drive. Now the scenario has been changed. So power electronics has to take care of both load dynamics as well as source dynamics. So it is a candidate to provide bidirectional power flow as well, right? So finding the solution in today's power system to decouple the components of active as well as reactive power to provide an artificial inertia or the virtual inertia, it is of great interest, should be further investigated, right? So finding the solution, ultimately it is not so easy in the today's power system. And finding the solution with a reduced system cost, in the cost effective solution, or increase the efficiency, and providing a decoupling of dynamics of energy sources, and moreover improving the power quality is of further interest that should be further investigated. As an electrical engineer, we have to concentrate on both load as well as source. Talk about the schematic of grid-tied solar PV system. So the PV array is composed of the PV model in series parallel combination. As the input parameters to the PV array is basically a solar irradiation temperature, that light energy will be converted into electrical energy. So that electrical energy is unregulated or uncontrollable, right? So that has to be interfaced with the grid via power electronics converter, as it is a candidate who provide an asynchronous interface. So the power electronics converter having the different topology as well as the components, and according to the topology and component, so that can integrate solar PV system with the utility grid. And while integrating the solar PV system with the utility grid, the power electronics converter with the suitable controller has to satisfy the grid connection requirement. So that grid connection requirement include active and reactive power control. Decoupled control of active and reactive power, that is very essential to control the frequency as well as the voltage. And moreover, it has to have an excellent transient response, and moreover, the grid synchronization, and moreover, provide the inertia to the system so that it can damp out any oscillation, and reactive power support as well, right? So the power converter with a suitable controller, that plays an important role in controlling the power delivery, and at the same time ensuring proper integration between PV and the utility grid. So according to the topology, as we could take the two-stage grid-tied solar PV system, as the solar PV array is connected with the DC to DC boost converter. So that boosts the voltage from low voltage PV into high voltage the DC link, and then the high voltage DC link will be inverted into AC with the help of three-phase voltage source PWM inverter. Then the controllable AC power that is being injected into the utility grid, right? So now it has a two-stage. So the PV array is basically the boost converter, it transfers the power from solar PV to the DC link, right? So the DC to DC converter is basically a source side converter, as it always interacts with the source. And another, the converter called the three-phase voltage source PWM inverter, is basically a converter that always interacts with the grid. So this is the grid interactive power converter, or the grid side converter. This is the source side converter that has been isolated with the DC using a DC link capacitor, right? So the control action that will be provided at the DC to DC boost converter, especially to extract the maximum power point tracking, right? To extract maximum power point tracking. And in the meanwhile, the control which is being employed on the three-phase voltage source inverter, so that has to satisfy all the grid connection requirements. So as you connect a three-phase non-linear unbalanced load at the point of common coupling, Of course, as the non-linear load is interacting with the grid, ultimately the grid current is going to be distorted. In addition to distorted grid current, voltage profile at the point of common coupling is going to be reduced, right? So the control algorithm which is being employed on a grid interactive or three-phase voltage source inverter, that has to ensure controllable active and reactive power for voltage as well as frequency control. That is very much essential. Yes, so now the control strategy, as the grid interactive power converter, it has to handle both DC as well as the AC parameter. So the DC parameter is an input parameter that is being derived from DC to DC boost converter in terms of DC link voltage, and the output parameter is basically an AC parameter. Basically, it involves with the grid parameter. So grid parameters are voltage as well as the frequency. So frequency must be maintained constant within the the variation should be within the acceptable limit that they say in the Indian grid. The frequency variation, it should be between 49.5 and 50.2. And moreover, voltage profile at the point of common coupling, that should be within the plus or minus 5 voltage range. So according to IEEE 519/2014 standard, right? So that has to be maintained with the help of AC control or the AC current as well as the AC voltage control on the inverter output side, and the inverter input side, the DC voltage control. So as the converter has to handle both the DC parameter as well as the output AC parameter. So ultimately we need an interfacing, the theory what is called instantaneous, the reactive power theory or instantaneous PQ theory, so that we are able to linearize the parameter to provide an independent control of both active power as well as the reactive power. That is very much essential because your system is highly coupled in terms of voltage and frequency. So there is a strong the phase angle between the voltage and frequency component. Any variation in the voltage that causes frequency variation, any variation in the frequency that causes voltage variation. So we need to have the theory so that the system can handle both the DC as well as AC variable, but still it can decouple both voltage as well as frequency component. That is what here, with the help of this theory in terms of stationary reference frame in alpha beta, or natural reference frame in ABC, or rotating reference frame in DQ, we are able to handle both AC as well as the DC parameters. Still, we can make it linearized, right? So AC power control, as you are, AC power control and the grid converter. So that can act as a grid feeding device or a grid forming device. So manage the DC link voltage. If there is not a DC to DC converter in charge of it, still it can inject that controllable AC power into the utility grid in terms of active as well as the reactive power. So the third option is the operation of grid supporting device in terms of voltage, frequency, or the power quality, right? So as far as the harmonic limits for the PV inverters is concerned, in Europe we follow the standard called IEC 61727 standard. IEC stands for International Electrotechnical Commission, that has been based in Geneva, right? And in the US, there is the recommendation IEEE 519/2014 standard. The recommended practice and requirements for harmonic control in electrical power system, including steady state operation. And for IEC, that is exclusively for the industrial operation for both steady state as well as transient. Okay, so still we have another standard, IEEE 1547 standard for the DER integration with the capacity up to 10 MVA. So whatever the standard you follows for grid integrative solar PV system, still the limits imposed by the standard has to satisfy the total harmonic distortion of the grid current. That should be always less than 5%. See the individual harmonic order as well as the distortion limit. Still, it should have distortion with the maximum of 4% for the 3rd order through 9th order, and it should be less than 0.6% having the frequency order from 23rd till 33rd order. And still now I could see the recent literature that still the harmonic presence in the converter above 33rd harmonic as well. That harmonic is what is called a supraharmonic. So still it can cause EMI or EMC problem associated with the magnetics in the power converter. Still that has to be investigated further. Yes, now the control structure, as I told you that the grid side converter is the component who satisfy the grid integration, or who satisfy grid connection requirements. So that has a cascaded control loop, basically an internal current control and outer voltage loop. So internal current control loop is basically regulating a grid current or inverter output current, because the inverter has to be protected against any overcurrent, because the inverter is designed to carry the rated current of the grid. If the grid current exceeds the rated current of the inverter is going to be overloaded, and hence the switches may be damaged at any cost. That is what. So in order to protect the inverter switches against overcurrent. So the grid, the current regulation is very essential. So that has been, incorporated with the internal current control. And not only that, as the due to the PWM pulse width modulation control and the inverter, ultimately the inverter output current is not sinusoidal, right? So due to the modulation and a non-uniform switching, it may cause the non-sinusoidal current injection. So further, the control is necessary to, shape your grid current waveform as sinusoidal. That must be harmonic. That must be harmonic free. So that is possible with the help of internal current controller. Moreover, it has to be designed with a large bandwidth so that it can provide excellent transient or dynamic response. Right. In addition to that, and the external voltage loop is mainly used to regulate the DC link voltage control. Regulate the DC link voltage. Why? DC link voltage is very essential to balance the power flow between a solar PV system and the utility grid. So if you are unable to maintain the power flow between the source and the load is not matched, ultimately if there is no match between the source and the demand, or ultimately it causes the DC link voltage profile that degrades, and again it has a problem of the frequency, right? So the frequency regulation is possible by active power control with the help of DC link voltage control, right? And moreover, that has been designed with low dynamics. Still, it won't be a problem to affect the overall system dynamics. In addition to that, it has a DC link voltage control cascaded with inner power control as well, and a variety of controls. Structure has been proposed in the in the grid interactive PV. Grid interactive power converter, and still the very universal controller what we use is basically a cascaded controller, internal current control and external voltage control. And the system architecture for the grid connected solar PV system as the solar PV array, and that generates a DC power, and that will be given to the DC link and via DC to DC boost converter. So that DC to DC boost converter that transfer a DC power or the solar PV power to the DC link from the low voltage PV to high voltage DC link. So it is basically boosting up the voltage, and moreover he is a candidate to transfer the maximum power transfer, maximum extracting power with the help of maximum power plant tracking, right? So that will be done here with the ARM Cortex M4 microcontroller, and so that it sends the PV voltage and PV current, and according to the algorithm based on incremental conductance method, it is able to generate the PWM pulses to the MOSFET so that you are able to achieve maximum power plant tracking, so that you can extract maximum possible power from the PV system that will be given to the DC link, right? And again, the DC link, the power available at the DC link at a high voltage, that will be, inverted into AC based on the line to line 415 volt. So that will be inverted into AC. Then the inverted AC or controllable AC is, feed into the utility grid in the form of active as well as a reactive power through breaker and interfacing inductor. So as we provide and control algorithm to the voltage source inverter for internal current control and outer voltage control loop, so basically it has a control circuitry. So that control circuitry includes voltage and current sensing element, as well as the amplification unit and the blanking circuit, as well as power supply unit, including isolation. So we are able to, generate the PWM pulses to the, three-phase four-legged inverter, so that you are able to achieve the desired control. You are able to apply your implemented control algorithm so that you can achieve your objectives. That is what. So here, the control algorithm is being implemented in the MATLAB Simulink, and with the help of the MATLAB Simulink file, according to your algorithm. So then once you run the simulation, that is able to generate the PWM pulses that will be connected with the host PC via, the DSpace 1104 interfacing card, that will generate the corresponding PWM pulses to the, the analog circuitry. Then again, that will be interfaced with the real, driver circuit. So it is able to generate the PWM pulses to the, the four-legged voltage source inverter, so that your control algorithm can be easily implemented without knowing any assembly language or any software literacy. That is what. So even any electrical engineer without knowing any software or any assembly language, still you can implement in the real time with the help of 1104 interfacing card, the digital signal processor. Right. So here the design of each subsystem, as you are designing a solar PV array, and it has been designed for 13.5 kilowatts and having series parallel combination of the solar panel, so that we could be able to design for 13.5 kilowatts of power. The DC power. I'm sorry, the K should be small letter. Right. So the calculation of DC link capacitor, as you are transferring 13.5 kilowatts of the solar PV power to the DC link, and ultimately the DC link capacitance calculation is very much essential. As you are transferring 13.5 kilowatt, still the DC link voltage has been designed with the 690 volt, so that you are able to I mean, invert 690 volt DC into 415 volt line to line. That is what. So DC link voltage always should have a, I mean, higher rating than the peak to peak or line to line three phase AC voltage, as we employ pulse width modulation technique. So the DC link capacitor has been designed with the 2257 microfarad. Assume that the angular frequency component is about, I mean, 50 hertz, 314. Okay, and the VDC ripple, it would be around 20% of the rated voltage. And the determination of DC bus terminal voltage, as I told you, as you are as you are converting DC into AC, the line to line AC voltage would be around 415 volt three phase. I mean, according to our Indian grid standard. So the DC link voltage imposed 690 volt, because as you use a pulse width modulation, the effective DC link utilization is about 78.5%. So always DC link voltage should be at least 125% of the line to line three phase AC voltage, right? And the design of coupling inductor is very important, because the inverter output current should have, I mean, it has a DC component as well. So the DC component, it is injected, to the grid through interfacing transformer, and ultimately the transformer core is going to be saturated due to double frequency oscillation or due to a DC component, the DC offset. So sometimes the DC offset component may saturate your core, and hence there is an inherent generation of, I mean, second order as well as third order harmonic. So overall system performance is going to be degraded, and moreover the efficiency also decreases. That is what. And the interface coupling inductor is used to reduce the current ripple, DC current ripple on the inverter output stage, that has been designed with the 3.31 millihenry, assuming that the switching frequency of the inverter is about 10 kilohertz. And the DC to DC converter, as we use as the maximum power point tracker on the source side, it is basically extracting the maximum possible power array of 13.5 kilowatts. So as it has been designed, as it is boosting the voltage from 540 volt into 690 volt. So the boost converter designed with the duty cycle of 0.21, and moreover the inductance of the boost converter would be around 4.52 millihenry, assuming the current ripple were around 25%. So that is a very important thing, that while designing such converter, while designing the practical, design of the boost converter with the inductor is quite different from the theoretical study, because as the PV is highly an intermittent energy source, so variation of the PV array, voltage as well as the PV array current is a very, it is a wide variation. So ultimately it may affect the optimal design of inductor as well as the capacitor, right? So the description of the control strategy, that as we are, as you are imposing on the controller, the control strategy on the inverter, and ultimately as the input parameters to the inverter is basically a DC parameter called the DC link voltage, and the output basically then output voltage as well as the output current, the grid voltage and grid current. So as you have a power transformation to transform ABC to DQ, so that the DQ components are basically orthogonal in nature, as the D component, it is basically an active current component that designs the active power control, and IQ is basically a reactive power component or quadrature component that designs the the reactive power injection, right? So as the D axis as well as Q axis component that composed of average DC as well as oscillating AC components as well. So further, the ID is basically a D axis component, while you are transferring power from renewable energy source into the utility grid via DC to AC inverter. Ultimately, there is an existence of double frequency oscillation. So that double frequency oscillation, it also transfers the power flow from the DC link into the the AC grid. So the DC link capacitor, it has a double frequency oscillation. So and hence the DC link capacitor is going to be overheated due to double frequency oscillation. That is what your ID component is passed through the second order low pass filter, so that it will damp out, or it will filter out the double frequency oscillation, so that the DC link voltage will be ripple free. That has to be taken care of while designing a DC link capacitor. And let us come to the generalized DQ based control algorithm, as the PV array is a source of power, and the output power of the PV array is given to the boost converter. So that boosts the PV array voltage into the high voltage level to the DC link, and then the voltage available at the DC link, that will be inverted into controllable AC with the help of voltage source inverter with a suitable controller. Then the controllable AC power is being injected into the utility grid via interfacing inductor as well as the interfacing transformer, right? So as you connect a nonlinear load at the point of common coupling, say a three-phase diode rectifier load or three-phase thyristor based any the load which is being available in the laboratory. So once you connect such load at the point of common coupling, as it interacts with the grid, ultimately there is a distortion in the grid current, and moreover voltage profile at the PCB is going to be degraded. So in order to provide a controller, ultimately we need closed loop controller. So we sense the three-phase AC voltage as well as three-phase AC current, and moreover, as you are implementing maximum power point tracking and the boost converter, so we sense the PV current and the PV voltage that will be given to the incremental conductance based MPPT technique. So that will, I mean, take care of the pulse width modulation, the PWM generation to the boost converter, so that you are able to extract maximum possible power, right? As the control loop is, we apply the cascaded control on the outer voltage control and the inner current control. Outer voltage control basically it regulates the DC link voltage. So the DC link voltage is basically set as a reference of 690 volt. So that will be compared with the actual DC link voltage. Then the error will be given to the DC, I mean that ID component reference in the loop. And moreover, that the three-phase AC current is going to be transformed into ID IQ with the help of ABC to DQ transformation. Then we can have a low-pass filter as it has to filter out the, I mean, double frequency oscillation. Finally, you are able to generate ID as well as IQ star, right? And on the voltage loop, your three-phase AC voltage that will be, I mean, come up with two-phase, I mean, voltage values. So that will generate the IQ component. So IQ component is basically responsible for the, I mean, the reactive power, I mean, generation or the reactive power injection during steady state. When the grid is under steady state or balanced, definitely need the support of reactive power. So IQ is assumed to be 0. So this contributes certain reactive power injection when the grid needs the support of reactive power. So that time IQ is not equal to 0. So then the components of ID, IQ that will be transformed to again the clock transformation with the ABC. Then we are able to generate the, I mean, the reference current ISR, ISY, ISB star. So I mean three-phase reference current. So that has been generated based on the control algorithm that is being employed on the inner current control and outer voltage control loop. Then that reference current is compared with the actual three-phase AC current that is being sensed by the sensor. Then it produces an error. So that the error current is given to, I mean, the inverter, I mean, the reference current that is being given to hysteresis current controller. It has been designed with the bandwidth of plus or minus 0.5 ampere. Then it is able to, I mean, control the current instantaneously between lower and upper threshold. It is able to generate the PWM pulses to three-phase, I mean, four-legged voltage source inverter, so that you are able to, I mean, achieve, I mean, your objectives. That is what. And moreover, as you're transferring DQ to ABC, this is the, I mean, transformation called the path transformation. You can use that. And while for such a transformation, always you need to, I mean, always you need to estimate or extract the, I mean, the phase component, what is called the synchronizing angle, that is called the phi. So this phi, extraction of phi is very important. That is possible with the help of synchronization, I mean, the adaptive phase locked loop. So because so whenever three-phase AC load is connected, non-linear load is connected, obviously your three-phase, I mean, grid current is distorted. So extracting the fundamental component when the grid is under abnormal condition or distorted condition, distorted grid condition is very difficult. That is why we propose an adaptive phase locked loop, so that you are able to precisely extract the value of phase angle phi that is being relevant to the fundamental phase angle called the 50 Hz component, so that you are able to implement your desired control algorithm. So that is a separate research area. The grid synchronization of distributed power generation with the help of adaptive phase locked loop is another research area that has to be further investigated. So this is the synchronization tool as we proposed that. So as the three-phase AC voltage will be transformed into DQ, so that you are able to estimate both magnitude as well as the phase angle. And with the help of compensator, as the PLL composed of the phase detector, loop filter, and voltage control oscillator, we are able to extract the fundamental component of the phase angle. So that is essential to, I mean, generate the reference current in an accurate way. Okay, this is a three-phase instantaneous voltage composed of R phase, B phase, and in phase with 120-degree phase angle, right? And this is the DC link voltage control loop. As your the DC link voltage control is very essential to maintain the power flow between the source and the load, as it provides the balanced power flow, so that you are able to regulate the grid frequency, right? So that has to be designed in a closed loop manner, so that the reference DC link voltage set as a, I mean, 690, that will be compared with the actual DC link voltage that is being sensed by the sensor. Then that will be given to the control loop. The designed with, I mean, optimal. Yes, please. So optimal gain value of Kp and Ka, you are able to regulate the DC link voltage in a precise way. So the corresponding transfer function between the DC link voltage and the reference DC link voltage given in the equation number 19. And as you are regulating a pole voltage, I mean the AC voltage, that has to have an instantaneous three-phase voltage of 415 volt, line to line. and it should have only the fundamental component. And you can see, as you are transferring power from inverter to the grid, so you assume that it is like a power system there, and there is sending end voltage is the V inverter at an angle of delta, and the receiving end voltage is the V grid at an angle of 0. So you are transferring power from inverter to the grid via interface inductor having a reactance of X. So this is the corresponding, active power being transferred from inverter to the grid, as it is a multiplication of inverter voltage and voltage with the grid voltage, and due to the phase angle difference between these two, there is a power transfer from sending end voltage the grid voltage, and moreover the power transfer is inversely proportional to the inductance reactance that has to be designed to the load, right? And where delta is the load angle. Okay. Yeah, and this is the incremental conductance method. As I told you that the power being extracted from the PV array, that largely depends on the irradiation and temperature. So the maximum possible power extraction is not straightforward. Ultimately, we have to use a DC to DC boost acting as an impedance matching device. So you are able to match the load impedance with the source impedance, right? So that is what, as the point at which we are extracting maximum possible array is available at the slope here. That is the point is MPPT, right? So now the change in voltage with reference, the change in current with reference to change in voltage, that must be always 0. It implies that the point at which the equilibrium condition satisfied, so that you are able to extract maximum possible power, right? So the slope can be either in the negative slope or maybe in the positive slope. That depends on the change in current with reference to change in voltage. That is what this technique is a very simple technique. You are able to observe the maximum power point tracking with the help of incremental conductance method, right? And this is the laboratory prototype that is being fabricated in the laboratory, and it has all type of all components including power circuitry and control circuitry and other measurement setup and all. And you can see the steady state response of the system as without any controller on the inverter, and you can see the three-phase AC voltage is sinusoidal, but as you connect a three-phase diode bridge rectifier load at the point of common coupling, you can see your grid current or supply current is distorted. You can see the load current profile. It is like a stepped wave because we connect three-phase diode bridge rectifier load, right? And due to the nonlinear load interacting with the grid, and your grid current is distorted. So as you propose a controller with active harmonic filtering operation, it will treat your shape current waveform as a sinusoidal, and moreover it can have a good dynamics when there is a sudden change in current from 28.66 ampere to 10.66 ampere. So throughout the cases, and you can see the DC link voltage is constant, and it always follows the reference trajectory of 690 volt. So it shows that the dynamic response is excellent, and moreover the compensating current injected by the inverter, the response is like this. So there is no control. Ultimately, there is no compensating current being injected by the inverter, so that your grid current waveform remain non-sinusoidal. That is what. And during such situation, as the active, proposed control strategy try to shape your current waveform as a sinusoidal, it is trying to forcefully reject the lower order harmonic component. Your grid current waveform remains sinusoidal, and it is in phase with voltage, and hence there is a demand of unity power factor operation. And you can see the dynamics of change of the active power at this phase, and the supply power is reduces from 20.9 kilowatts to the 7.41 kilowatts. In the meanwhile, for meeting the power the power demand, so your PV power increases to 13.49 kilowatts. 13.5 kilowatts of maximum. And this is the transient response whenever the sudden decrease in current from 34.37 ampere to 15.85 ampere. Still throughout the case, load current profile is not sinusoidal because we connect three-phase diode bridge rectifier load, and the load profile is like a stepped one. And still, and after applying a control on the three-phase voltage source inverter, the compensating current that is being injected by the inverter is this much, and accordingly it will try to shape your the grid current waveform sinusoidal, and having the THD of less than 5% as per IEEE 519/2014 standard. And throughout the case, you can see that the DC link voltage, it maintains constant with the reduction in steady state error as well as the peak overshoot, and moreover it always follows the reference trajectory of 690 volt. And see the power factor is become unity because this the input current is the grid current is in phase with the grid voltage, and you can see the dynamics of change in power of the supply power from 24.82 watts to 11.44 watts. In the meanwhile, the power sharing, as the PV is contributing certain amount of power, about 13.37 kilowatts. And you can see throughout the cases, even with controller or without controller, when you connect a three-phase diode bridge rectifier load, you see there is no existence of source, the neutral, source neutral current, because as we use the fourth leg of the inverter that provide an alternate path for the neutral current, and hence the neutral current is suppressed in the inverter fourth leg itself. So it is not flowing towards the zero neutral. So the zero sequence component is absent, and ultimately there is no existence of third harmonic current as well. And you see the load current profile and the load neutral current, still it flows and oscillates, but the source neutral current is zero, so there is no overheating of the neutral wire of the source side or the grid side. And this is the dynamic response of the system under solar intermittency, that as whenever they change in the irradiation, ultimately there is a change in active power. As I told you, the change in irradiation, it causes change in the PV current, ultimately it affects the solar power production. And you can see the change in irradiation, it causes the change in the three-phase AC current, and ultimately then it can't be met by the load, so that the additional PV is supplying certain amount of power, so that it is able to provide proper power sharing, right? So it is contributing for the energy management. And you can see that the compensating current by the inverter is about the 18 ampere. Still the DC link voltage profile, it remains same, and it follows the reference trajectory, right? And you can see the dynamics in the change in active as well as the active power of the PV, as well as the the supply. And moreover, throughout the case, as the irradiation is getting changed, then ultimately change in the current as well as change in the power. And you can see the experimental result for active harmonic filtering operation. As a three-phase AC voltage is sinusoidal, but as you are connecting a three-phase diode bridge rectifier load, the source current is distorted, and again it is non-sinusoidal, right? By proposing the active harmonic filtering operation with the inverter control, and it is trying to shape your grid current waveform sinusoidal, and again it is in phase with voltage, so that your the power factor is become unity, and moreover the power quality problem can also be mitigated, right? And you can see the compensating current and what is available, and the compensating current by the inverter, and moreover the three-phase load current profile is available. It is stepped as a staircase, right? See, it is trying to shape your grid current or supply current waveform sinusoidal, and again it is at par with the supply voltage, and hence there is a strong demand of the power quality, right? And still your load current profile is still a stepped one. And you can see here, as you are connecting three-phase diode bridge rectifier load, you see three-phase current waveform remain non-sinusoidal, and due to the non-linear unbalanced current, and hence there is a circulation of neutral current. As you might be knowing, the neutral current is basically an algebraic sum of three-phase AC current. When it is balanced, there is no neutral current. When it is unbalanced, ultimately the current flows. So that current has to be neutralized to avoid overheating of the neutral wire. We propose the fourth leg. So fourth leg, it take care of a neutral current circulation, neutral current suppression. So the neutral current, it becomes zero on the grid, and moreover the three-phase AC current, it becomes sinusoidal, right? So throughout the cases, you can see that three-phase AC current is in phase with the three-phase AC voltage, and ultimately the power factor becomes unity. And this is the multi-purpose, it is a multi-purpose or multifunctional inverter with active power sharing. As I told you, during change in the irradiation, still the solar PV is also contributing for the active power. You can see the active power, by the solar PV is about 102 watts, and the three-phase AC grid power is about 110 watts, and ultimately the demand in active power reduces to 56.7 watts. So that it also contributes for active power sharing, in addition to the active as well as the reactive power control. And moreover, throughout the case, the DC bus voltage is maintained constant. By employing an outer DC link voltage control, right? And all the cases, you can see three-phase AC current waveform remains sinusoidal, and it is in phase with voltage. Okay, you can see the the harmonic spectrum of the grid current, and without any controller, the THD of the grid current is about 26.5%, but with active harmonic filtering, it has been reduced to 4.67%. And further, with the multifunctional inverter operation, it has been reduced to 4.40%, as it satisfies IEEE 519/2014 standard. So throughout the case, you can see the inverter, it injects only the fundamental component having the fundamental frequency of 50 Hz. Rest all the harmonic components are forcefully rejected based on the control algorithm which is being employed on the grid interactive power converter. Right, this is the comparison table for the different phases without any controller, or with OPM controller, and with multifunctional inverter control. You can see throughout the cases, the power factor, it become almost unity, and moreover the THD of the grid current, it is always less than 5%. And this is the hardware development and experimental analysis with the step change in the nonlinear load. So there is a sudden increment in load and a sudden decrement in load. So you can see throughout the case of sudden increment in load or sudden decrement in load, with the help of the external or outer voltage loop control with the precise tuning of PI controller, it is able to maintain the DC link voltage constant as at par with the reference voltage of 690 volt. See the current value changes during sudden increment in load or sudden decrement in load. So throughout the case, load current profile still it is stepped and it is a non-linear load, but still your supply current waveform become sinusoidal. Okay, that is what. So throughout the case, the DC link voltage is maintaining constant, and moreover there is no circulation of neutral current. And this is the summary of experimental result with the simulation as well as the experiment. And as for a laboratory prototype, it has been scaled down to 60 volt of supply voltage with 50 hertz. And these are the different design parameters of the proposed system. So that we have taken a case study of 500 watts PV panel. So that has been integrated with the utility grid. So that how we employed a different controller or the advanced controller on this three-phase voltage source inverter, so that we are able to integrate such renewable power generation with utility grid. So that has been done. So that has been published in IIITD, and we have published a number of papers with this advanced control on the grid-tied solar PV system, and even we published the paper in IEEE transaction industrial applications as well. And the overall, the summary of the proposed study is to meet the grid connection requirements. That grid connection requirements include active as well as intact reactive power control and unity power factor operation and sinusoidal grid current injection into the utility grid and external transient response, and moreover improved power quality as well. Right. This is the another control technique that we have been proposed in the three-phase voltage source inverter powered by a solar PV array through DC to DC boost converter. Here, the three-phase voltage source inverter is shunted across the point of common coupling. So, and hence this act as a DStatCom or can be act as a active power, shunt active power filter, so that it is able to contribute for the power quality improvement. And here, three-phase voltage source inverter is powered by a solar PV array. So it not only contribute for the power quality improvement, it also contribute for the active power sharing when a three-phase diode rectifier load is connected at the point of common coupling. So because when the load demand is not met by the inverter, then additional the surplus or the additional power is being supplied by the solar PV array through boost converter as well as the inverter. So this is the complete the schematic diagram, and this is the control technique what we proposed. With the help of this active current control with the feed forward control loop on the inverter, we are able to precisely extract the fundamental frequency component or active current component, so that we are able to generate precise reference current. So the control algorithm can be easily implemented, and moreover control is very simple, that we uses only the summer and the integrator on the each loop of the current, so that the control is very simple, that can be easily implemented in any digital signal platform. That is the contribution as we have done. And the configuration of DSpace, as it is available with DSpace 1104 control card. So we are able to develop the control algorithm on the MATLAB simulate. We are able to interface with the real-time controller card with the driver circuit, so that we are able to generate the PWM pulses to the three-phase voltage source inverter, so that we can implement the control algorithm that has been done in the real time as well. And this is the same again transient response of the PV perturbations as as we have done for the PV perturbation as well as for the power sharing as well. The same the case study we have taken, and without any multifunction inverter control, you see the grid current waveform is non-sinusoidal. With the help of the multifunction inverter control, your three-phase grid current it becomes sinusoidal. And see, throughout the case, the load current is it is a stepped one, because we connect three-phase diode bridge rectifier load with RL, and moreover the compensating current response is this is the current which is being injected by the inverter. And I see the DC link voltage controller, it always follows the reference trajectory with the excellent steady state response as well as transient response. See, as the proposed controller ensures the sinusoidal current injection, the grid current it becomes sinusoidal and it interfaces with voltage. So there is a demand of unity power factor operation of the grid, so that the reactive power burden is largely reduced with the help of the inverter control. And moreover, the power sharing is being employed with the help of solar PV, and how the power sharing is being done with the help of solar PV system, that you could see from this result. And this is what the DC link voltage stabilization has happened with the the previous controller that is being proposed in the literature. You can see the peak overshoot as well as the the steady state response, but still with the help of the feed forward control loop and you see the DC bus voltage stabilization that can happen with reduced peak overshoot as well as reduced steady state error. So that is what the the contribution bias that has been published in IEEE transactions and industrial applications. Okay, this is the the different experimental result for the different case study. As you connect a three-phase non-linear load, see the supply current waveform, it follows the three-phase non-linear load, and hence it is distorted. So by proposing a control strategy, now the grid current waveform becomes sinusoidal with the TH3 less than 5%, and moreover your three-phase current waveform is in phase with voltage, and hence the power factor becomes unity. So there is a strong reduction in the reactive power demand, right? But still throughout the case, the load current waveform is still stable one, right? And you can see that there is a neutral current because as you connect a three-phase diode bridge rectifier load, ultimately there is a neutral current because of unbalanced load. And still we propose a fourth leg. So fourth leg, it will take care of the neutral current circulation. So ultimately it becomes zero. Still the three-phase AC current becomes sinusoidal and it is in phase with voltage. And see the the active power sharing in the manual, the THD of the grid current. See the without any controller, the THD it would be around the THD would be around 25.1%, but with active current control, and the THD has been reduced to 4.7%, and moreover, so it injects only sinusoidal current into the utility grid without with negligible harmonic current injection. Okay, this is the summary of experimental result that the multifunction inverter with multifunction inverter and without multifunction inverter, you can see the active power demand is reduces from 143 watts to 60 watts. It means 83 watts has been supplied by the solar PV array, and moreover the grid reactive power support has been reduces from 60.8 VAR to 5.99 VAR. It implies that there is a strong reduction in the reactive power demand by the grid, so that the power the power factor of the grid has been enhanced to unity. The source power factor, yes, it has been enhanced to 0.995. I mean unity power factor operation, so there is no demand of the reactive power, right? So the grid current magnitude has also been reduced from 4.3 ampere to 1.66 ampere. Ultimately, the overall system efficiency has been increased, and the grid current THD has been reduced from 25.1% to 4.7%. You can see the overall performance. We ultimately meet the objectives of the grid connection requirements of solar PV system with the utility grid. Okay, so the summary that the proposed solar PV system with a multifunction inverter, it feeds controllable active as well as reactive power into the utility grid, and moreover, it also acts as a shunt active power filter, so that filter out the unnecessary harmonic component which is being injected into the utility grid, and so that overall the grid current waveform it becomes sinusoidal and having the THD less than 5% as per IEEE 519/2014 standard, right? And additionally, the fourth leg of the voltage source inverter can effectively eliminate or neutralize the neutral current, so that it can avoid third harmonic current circulation by making the absence of zero sequence current component. Okay, so consequently, this enables the utility grid to deliver only the balanced sinusoidal current at the unity power factor. So the results presented here clearly illustrate that the proposed multifunction inverter with the control meet the TH3 requirement of IEEE 519/2014 standard. So that was the summary, and we have we are further investigating on the grid interactive solar PV system, especially during grid abnormalities and especially during fault conditions. So that is being further investigated. Okay, and these are the key references for our research paper. Those we came across the papers in IEEE as well as in the IET level, and further we are working to have a very robust solution for meeting the entire grid connection requirements. Okay, that is what. And I'm happy to inform you that as I'm an editor of the Electrical Engineering Springer Journal, recently I have floated the special issue call for papers on energy storage, design, control, and application in modern power system. As you might be knowing, Electrical Engineering Springer Journal is one of the oldest journal in electrical engineering category since 1912. And I'm a lead editor for this the special issue call on energy storage. Okay, so if someone is working on energy storage and its application in modern power system including renewable energy, so you are welcome to submit your paper to this prestigious electrical engineering journal published by Springer. The full manuscript due is 15 December and it will be notified on 30th March 2020. Concurrently, that will be published in June 2021 issue. Okay, all proposed papers must be submitted via the editorial manager online submission system. While submitting, you please select the candidate with the special issue energy storage. Okay, so thank you very much for your kind attention. Hope you might have enjoyed the session on grid interactive solar PV system. So I have come across the different components of grid interactive solar PV system, including fundamental and control as well as advanced control techniques as well. Okay, thank you again. And once again, thank you very much, Professor Gayadhar Panta, who has given an opportunity to share my knowledge on the grid interactive solar PV system. Thank you very much. If you have any doubt, please let me know.
Thank you, Dr. Chitti.
Yeah.
It's a really means a constant effort for last 3 hours from 10 to 1. Continuously you are delivering the lecture. That is really helpful. But you have accepted our invitation also just day before. That is also one of the pleasure for us that under crisis you have taken the task. And hopefully all the participants are enjoying. And we have started with the PV integration, and Dr. Chitti has elaborated completely over the control system and how the power quality is in control, or the power quality improvement using active power filter. And the basics also he has covered very nicely. I was also present that time, how the PV means a PV operation, how the MPPT, all those things. He has given a clear vision about the PV integration and control. Thank you. Thank you, Dr. Chitti. If any questionnaires are there, I can ask my PhD scholar if anyone is having.
Yes, sir. So I'll read one by one question, sirs.
Yeah.
We'll take the questions now, Dr. Chitti, sir.
Yes, Professor. Yeah, please.
Just
Okay,
see that. What is the question coming?
The first question is how the inertia problem will be handled in solar PV system.
Okay.
Inertia, virtual inertia.
Now, how the inertia problem will be handled in solar PV system.
Okay.
Yes. What was the question?
How the inertia problem will be handled in solar PV system.
Yeah, so you see, in a solar PV system, as basically the solar PV is an inertialess system, as basically a static power source to convert light energy into electrical energy. Obviously, it doesn't have any 0% in inertia. Okay, so that is possible by incorporating a battery energy storage. I mean, in addition to the solar PV. So that may be an important thing for the standalone system. See here, we are feeding power to the utility grid constantly, and whenever there is an irradiation of the power, right? So for grid connected PV system, it doesn't need any kind of inertia, as it is continuously feeding power to the utility grid. But when the grid is under abnormal condition, say when the grid is under fault condition, then we have to think of how to provide and the support of reactive power with the help of energy storage, right? So that here we assume that there is a constant irradiation that is being available during daytime. We are able to harvest the power. We are able to condition the power that is being injected into the utility grid. Yeah, so that is what we do not think of the energy storage design. That is very important for the standalone system. Maybe I think that will be presented by our Professor Gayadhar Panda, maybe in his session. What I feel.
Okay, thank you. Yes, Kavala, any other question or will conclude?
Yes, sir. So thank you, sir. Next question is how to choose the size of the filters in these kind of systems.
Yeah, the size of the filter, again, there are two things. So the size of the filter means basically an inductor filter that is strongly dependent on the switching frequency, right? As it is a grid connected inverter system, so we no need to go for the switching frequency above 10 kilohertz. Even the response is very good with the sinusoidal current injection. Even the switching frequency is 5 kilohertz, so that won't affect the overall system dynamics. So as far as the grid connected inverter system is concerned, you can go up to the 10 kilohertz frequency, still the dynamics won't be compromised there. So accordingly, you can design the filter. Even the filter design itself a great task. It has a different kind of classification, or the different classification of filter, like a LC filter, LCL filter, and LCL filter with the active damping and the passive damping. And that again, it contributes for the overall system dynamics. So that has to be further investigated. That is not a straightforward to choose the particular value of inductor.
Yes. Okay. Yeah. Thank you, Dr. Chitti, sir, and hopefully all the participants have enjoyed. And there may be more questions, but we cannot take all the questions.
Yeah, yeah. And
You can check one or
yes, if you have any doubt, dear participants, you
yes,
can send me an email.
yes,
Definitely,
yes.
I
You
shall
can drop
clarify
a
your
mail.
doubt. Yeah.
You can drop a mail. You can interact. Okay.
Okay.
These are the small questions which
Okay.
means easily you can find out from the literature also.
Yeah, yeah, yeah. That is true,
Okay.
Professor. Yeah, yeah.
Okay.
Mm.
Okay.
Okay.
Thank you. Thank you very much.